Have you ever heard the phrase meeting specifications for electronics? Have you ever wondered how you select parts? This process seems to be skipped over in college or any electronics class. I don't really think it's done on purpose because this generally comes with experience. Generic parts such as resistors, capacitors, and inductors will have guidelines for selection that really only depend on three things: wattage, voltage, and current. In fact, most integrated circuits, even the more complex stuff, can be selected using these three fundamental measurements. Yes, it gets more complicated when you get into like data transmission, digital logic, and frequency, but that's not really what we're covering today. I will provide an interesting tidbit about frequency ratings and other software-related idiosyncrasies. These generally don't cause systems to fail catastrophically in the same way that power, current, and voltage ratings do. These are typically what I would call recoverable or tunable issues. On a technical level, when people say that they've bricked a console, they usually haven't damaged physical hardware at all. The electronics are operating within their voltage, current, and power limitations. What is actually broken is the software state, either firmware corruption, locked status, or it's just stuck in a configuration that prevents correct booting. I'm going to reiterate a point that I've made in a previous video in the top right about supplies, because it's critical to understand this. The rating is the rating is the rating is the rating. Yeah, it's funny wording, but people actually think you can squeeze out just a little bit more current, voltage, or power out of a supply. You have a supply that's rated for 5 amps. Can I squeeze 5.05 amps out of this? That is the kind of question that I've actually heard before. The answer is basically no. You will probably burn it out even if it's just a little bit over. Granted, it may not happen right away if it's a tiny bit over, but once you exceed the limit, it's really unpredictable if you'll have catastrophic failure over time or immediate, what I call magic blue smoke. Every device has thermal limits. A 5 amp supply certainly can deliver 5 amps, but if you run it continuously, it will run hot all the time. Heat is a great enemy of electronics. It accelerates aging and shortens the life of components. There is a similar concept in mechanical engineering, actually, called creep. You can hang a weight at the maximum rated load of a metal beam, and maybe even just slightly under that. But if you leave it there for an extended amount of time, the material actually slowly deforms and can eventually fail. This is why a lot of electronics engineers use a safety margin of 70 to 80%. This percentage kind of varies depending on application, but it's just a rough estimate. This is to allow kind of a breathing room for your application. Let's use basic examples that students often overlook: wires and resistors. If you are in a lab and you're just given resistors and wire, it probably won't overheat on you because they have been carefully selected for demonstration. Leave a student on their own, however, and they just go grab random parts, well, that becomes an issue. I've seen a fair share of people in the lab just pick thin wires and any value resistor thinking, I can push 1 or more amps through this, no problem. The math just works, right? It wasn't just them. I'm also describing myself because I'm fairly certain I've caused wires to burn up before or cooked a handful of resistors by accident. This newfound frustration might falsely reinforce that you didn't understand the lesson properly. because of something that wasn't explained to you. You have to consider the wattage rating of a component. These are max ratings often found in datasheets for a resistor or any component. Wattage is voltage times current, or current squared times the resistance. You can use the current you calculated when doing Ohm's law or any circuit analysis as that value to figure out the wattage consumption that your component will draw, or you could just figure out what the maximum voltage your resistor can handle. The formula for that is voltage equals the square root of power times resistance. So let me grab a 10K resistor here in just a second. So this right here, this tiny itty bitty part, hold on, let it focus here. Hold on. Focus. Yes, so this tiny part at most is rated for 1 watt. Let me show kind of why I think that. So this resistor is approximately 2.2-ish in diameter. So if I know how to navigate DigiKey's website pretty well. I just like to use this site a lot. So if I select anywhere from, I'd say, close to 2.2, maybe even 2.3, because I'm not entirely certain on the measurement, I'll get a value from 1/6 watt to 1 watt. I think I usually buy a minimum of 1 watt for this resistor. So, and the way that you can figure out the resistance value, the colors on here are brown, black, orange, and gold. There's a calculator on the DigiKey website under resources, tools, and conversion calculators, by the way. But anyway, so I'm thinking that this is probably a 1 watt. That's usually my default when I buy components. So back to the explanation here. The maximum voltage that I could probably safely use is the square root of 1 times 10,000, which is 100 volts. There might be more information in the datasheet that describes something called a limiting element voltage too, which may be lower than the calculated voltage that I just gave. Always go with the lower value. We could also put a 70% rule and say that 70 volts is probably safe. We can confirm this with the power equation. Since 100 volts is, let's say that we do go with the 100 volt value. Since 100 volts is the running voltage and the resistance is 10K, that gives us 10 milliamps of current based on Ohm's law. 10 milliamps of current times the voltage of 100 is 1 watt, the exact value that we just discussed. This does mean that the resistor would run really hot though if I were to do 10 milliamps all the time with that voltage. As for wires, that's a little bit simpler. That's a hard sentence to say. While wires do have resistance, it is extremely small and takes a very long length to add up significantly. Generally speaking, a small 20 to 22 gauge wire can handle 5 to 6 amps according to UL standards. For those that don't know what UL is, it stands for Underwriters Laboratories. They are a regulatory testing agency that gives a bunch of parameters for safely testing components. I'm sure that you've seen UL labels on power supplies before. Anyway, the reason that this matters, larger resistances are going to have a wider operating voltage, because that's just how the math works. Smaller value resistors won't be as forgiving for voltage ratings because of how the equation is. This is why resistors get pretty large when you go over 1 watt. For example, if you wanted to run a full 5 amps through a 5 ohm resistor, that's 5 squared times 5 ohms, the power required is at least 125 watts. You're not going to find a throw-hole resistor that can handle that. It becomes quite huge. Let me show that really quick, actually. So back on DigiKey, I actually went through the through-hole category, and let's say that I want 5 ohms. I'll switch this to ohms here. I just kind of give it in between here. Apply. Just select 5. I don't really care about the composition. I just want to see if there's anything that matches what I'm looking for. 100 watts is the maximum. This is not going to cut it. So there's a different category called chassis mount resistors. Think like boxes or like metal. They're called chassis. You literally screw down these larger parts onto a metal plate or chassis, literally. That's all that means. So in this category, you're going to have a lot higher values for power. Actually, let me just show you the process really quick. It's the same kind of thing, but so let's say 4 to 6 again. We're looking at 5 ohms, and it needs to meet or exceed, that's important, 125 watts, because that's what we calculated, right? Yes. 5 squared times 5. 125 watts. So 120 watts won't cut it. We can do 150 to maybe 200, just as anything really. You could go all the way up, but these get really big, so let's just do up to 200. So I'm going to just choose ones that have photos. Of course, these aren't 100% representative, but whatever. It's for our investigation purposes. These things are big. They're not small. This one measures 1.5 inches by 0.9 inches. Oops, let's go back a sec. This one right here, that measures 4.3 inches by 3.1 inches. It's huge. This one measures 6.5 inches by 2.36 inches. Massive. And yes, so basically you're going to have chunky, big resistors in order to handle that much power. Let me just go back to my screen, to my full video. Actually, I just kind of want to prove this really for a second here. I'm going to whip something up in LTSpice. Sorry, give me a second. So if I do a 25 volt source, and we do a 5 ohm, let's say, I mean, power rating won't really change how it simulates, but just for sake of consistency, we may as well do 200, and then we need a ground. Okay, then we run it. Let's say just 3 seconds. So we are going to get the full 5 amps, the power, 125 watts. So yeah, I don't think LTSpice, let's just say if I change that to 50, I don't think it would change actually. No. So it's not LTSpice does not take into account thermal models, so let's just go back to 200. Yeah, so let me just go back to my screen, to my webcam, I mean, sorry. So, yes, you're going to have huge resistors if you want to handle that much power, because you need it to handle a lot of heat. A tiny resistor like that, like this, it's not going to handle that much. 10 milliamps. So going back to that power supply video, your circuit will only draw as much as it needs, of course. This is why you need to be aware of the total amount of current the combination of your parts will add up to properly select a power supply. Some parts, like LEDs, need series resistors because they have a very low, what's called a dynamic resistance. Without current limiting, they will try to draw as much current as the supply can give and overheat almost instantly. I'm sure that you've blown up LEDs before, because I have. Hopefully this has helped you understand a little bit more on selecting parts and realizing that everything has limits as to how much power that they can either produce or sustain or stand. A power rating is a good way to say that. I know I didn't cover everything, but that really involves your own level of discovery when you develop an electrical design. Like, comment, subscribe, and remember, think outside the box and stay wise. See ya.